Hello everybody, this is Suvarchala working as an Associate Professor, Department of Computer Science and Engineering at IARE. As a part of the Designing and Analysis of Algorithm lecture series, in this session I would like to discuss the second technique for construction of minimum cost spanning tree. Kruskal's algorithm is the second algorithm used for construction of minimum cost spanning tree. So the Kruskal's algorithm used to construct a minimum spanning tree. The main basic idea is it is greedily construct the MST. Remember, always we are using the greedily construction process. This indicates that your MST may not be minimized cost spanning tree. Sometimes it happens. And in case of Kruskal's, instead of considering as in case of Prim's algorithm, instead of considering our vertices, we will consider edges. So in case of Kruskal's, go through the list of all edges and make the forest of all vertices of MST. That means initially your graph consists of n vertices, then each vertex is considered to be as a tree. Right? So that is forest of trees. Forest, all of us aware of that. Set of trees is known as forest. At each vertex, sort the edges. Edges are sorted, and whichever the least cost edge is, that is included in our spanning tree. Included in our spanning tree means the respective trees are going to be unioned, in other words, or merged, in other words. So the edges with the smallest weights examined and possibly added to the minimum cost spanning tree before the edges with the higher weights. That means while doing this process, the least cost edges are considered initially, and we are going on adding one by one least cost edges so that finally we'll get the larger values actually. The edges added must be checked whether it is a safe edge or not. What is meant by safe edge? Safe edge is an edge that do not disturb the tree property. What is tree property? Cycle formation. Tree should not contain a cycle. So by adding this edge, there should not form a cycle in our MST because it's tree, no? So that's how we have to check. How to check whether a cycle forms or not, that we'll discuss further. A special data structure is used for such type of cycle formation techniques. So this is the outline of Kruskal's algorithm. The steps are, first we have to construct a forest. Forest means a set of trees. In each tree, each vertex of your graph is one tree. That's all. So with each node in a separate tree, a forest is constructed. Then the edges are placed in priority tree. So in case of edges, priority queue or in a sorted order, whichever the way you would like to keep, you can keep. Or those are going to be sorted first, they will kept in a order so that one by one it will be keeping on adding to that. Depending upon the process which we are using, either priority queue implementation or a sorting of algorithm is used, that complexity will also include in our construction of the MST actually. So depending upon that, we always very cautious about choosing the process also. Now, this process is keeping on adding the edges is continued until number of edges added is n-1. Why? Because our spanning tree should include all vertices of graph. For example, n vertices are there in our graph. Our tree also should contain n vertices. Fine. Tree is connected, right? So that's why if it is connected means the number of edges must be n-1. So that's why when we are keeping on adding edges one by one means by checking whether that particular edge is safe or not, automatically the respective edges are considered to be as added. n-1 means n vertices are added. Once n vertices are added means our spanning tree was got constructed actually. So we have to consider until the n-1 edges, we have to do the process, extract the cheapest edge from the queue. It forms a cycle, reject it, otherwise add. Adding means add it to the forest. Adding the forest means the respective trees are going to be merged. Adding it to the forest will join two trees together actually. So at every step, this will be joining of the two trees in the forest together, so that at the end there will be only one tree. So every time we are adding no, so that's because of that what happens, n minus 1 times this is executed. That is n minus 1 times edges are added. So that's why we will get a finally tree edge. We'll do one or two examples and how to check whether a cycle forms or not in this case actually. At the time of adding an edge, we will use a special data structure. Then I'll come back to the example. A special data structure known as a disjoint set data structure, which we have done a session on this disjoint sets actually. So in case of disjoint sets here, the sets which are doesn't have a common element, those are disjoint sets, and disjoint sets are associated with three operations: make set, find set, and union. These things we discussed, and also as an application of disjoint set, we discussed disjoint set operation, union operation specifies whether that respective edge forms a cycle or not actually. That means we will check if any edge UV is taken, we will consider find U and find V. What is the purpose of find algorithm? Find algorithm returns the representative or the set to which that particular vertex belongs to. That means find set of U means we will get the set representative or a set name to which that particular U vertex belongs to that. So when an edge is supposed to be added UV, let us assume that we will consider find set U and find set V. Similarly, we will use find set U and find set V. If both parents are same means here, both parents means here, both belongs to the same tree. Means if by adding this new edge, because already existing vertices are there, no two vertices, and we are adding a new edge means it forms a cycle. This property is going to be used by us in our forest for vertices constructing into a minimum cost spanning tree. So, what is the special data structure we are using? We are going to use here operations of disjoint data set data structure, which is associated with three operations: make a set, find set, and union. Make a set, it creates a new disjoint set. Find set returns what is the representative or the tree name of the respective vertex belongs to. And UV means union means here. Union means either the tree with having parent of U is a child to V tree, or V can be a child tree to E. That is, it unites the dynamic sets that contain UV, say SU and SV. That means normal union only. If it is in case of graphical representation of tree, one is added as a child to the other one actually. Now, these operations are used in Kruskal's algorithm to check by a newly added edge is safe or not. In other words, by adding that particular edge, a cycle forms or not actually. So this can be done through these operations. So that's why our Kruskal's algorithm complexity includes the complexity of these union find operations also. So that's why we have to implement these operations very efficiently so that the complexity of our Kruskal's algorithm can be minimized. Right? So make a set, find a set, and union. These are the three operations are there associated with our Kruskal's algorithm to check whether a cycle forms or not. Now we will consider here the graph example. Various steps are there. And first we will arrange all vertices in the ascending order of the edge weights. Ascending order of the edge weights means H1, HG is 1, CA and GF are having the weight as 2. Okay. And ABCF are having the weight as a 4. You please check here. Left side the weight is given here. And we are having IG. IG is with the weight 6 and CDIH are weight 7 and AH is 8 and ABC is 8, D is with 9, EF is 10, BH is 11 and DF is 14. Now we arranged all these vertices, edges. All these edges in ascending order of the respective weights. Some of the edges are having same weight, no problem, we will consider that further. Whenever we are finding this minimum cost spanning tree, if duplicate weights are available, the tree formation can be different, but the minimum weight is going to be the same. Okay, the cost of the tree is going to be the same only. Even the duplicate edges are there. Of course, sometimes formation may be different actually. Now, what we are doing here, what is the key idea? Forest. A, you observe here, A, B, C, D, E, F, G, H, I. All these are trees. We are representing them in the form of a sets. Okay, so all these are individual trees and each tree is having one vertex. It's as a root only. First, which edge I supposed to add? HG. H belongs to which tree? This is the H. G belongs to this tree. Whenever an edge to be added, if both vertices are belonging to different trees, add it. Adding means here, the respective trees must be unioned. Adding an edge means the respective tree must be unioned. That means this G set, H set must be get unioned. That means add HD. Then what happens? My forest is becoming like this. GH and remaining things are as it is. A, B, C, D, E, F, I. Clear? Whenever an edge is added to be added, the edge vertices must belong to two different disjoint sets. If they belongs to two different disjoint sets, it can be added to my tree. Adding a tree means the respective disjoint sets must be unioned so that we will get the finally tree. What is next one? Either CI or GF. I'll take CI here. CI means C belongs to which set? C. I belongs to I. Both are belonging to two different sets. I can add. After adding, what happens? These two sets must be unioned. C set and I set. So that's why what are the result after adding CI? GH, CI and A, B, D, E, F. You observe. CI and becomes as a single set. Single set means here a single tree was generated. Okay. Now, add next edge is GF. 2 is no. G belongs to which edge? G belongs to here, to this edge, first tree. F belongs to another. Can I add? Yes, we can add. So while adding this, GH and F, these two sets are get unioned. So GHF, CI, you will get A, B, C, D, E. Next, what is the next set? AB. A belongs to A set, B belongs to B set. Okay, I can add. Then what happens? GHF, CI, AB becomes here AB and DE are there. Next one is CF. C belongs to which set? This set. F belongs to this set. Both are different sets. I can add. After adding CF, what happens? These two are unioned. So I'll get GHFCI. GHFCI. So what are the remaining things? AB. So this is after adding CF, GHFCI. These two are unioned. So I'll get ABDE as this. Fine. After adding AB, after adding CF, we got like this. Then next one is IG. I belongs to which set? This set. G belongs to which set? Same set. If both, now you observe this is. G belongs to which set? When I am considering IG, I belongs to the IG. You please observe the sixth step. So I belongs to this set. Again, G belongs to also same set. Both are belonging to the same set. By adding this, it forms a cycle. So that's why we are using considering ignore. Ignore means reject, in other words. So reject that particular edge. Then adding CD. How to add CD here? C belongs to which set? C belongs to here. C belongs to this set. D belongs to this set. I can add. Adding means you can union. After union, these two sets I'll get G, H, F, C, I, D. AB will be there, E will be there now. Clear? After CD, I have to check IH. I belongs to which set? This. H belongs to this set. I cannot add. So IH can be ignored. IH must be ignored because I belongs to and H belongs to both belongs to the same set, which cannot be added, because by adding this, what happens? It forms a cycle. So that's why we have to ignore it actually. Clear? Then next one is AH. AH, when we are considering A belongs to this one and H belongs to this one, I can add, I'll get a single set union. Now I got all these are one and E is another set. After AH, BC. BC I cannot add, ignore. Why? Because B, both C belongs to the same set. Please check except E. All others are belonging to the same set. So DE, yes, I can add. Why? Because D belongs to this set, E belongs to this set. I can add, I can make it as a union. Now I got only a single set. I can stop there actually. Once I got a single set means all necessary edges are added. I got a single set I can consider. Even though you are considering the remaining edges, it doesn't make any sense to us. Please observe, EF belongs to the same set, cannot be added. BH belongs to the same set, cannot be added. DF belongs to the same set, cannot be added. A single set available, no? So that's why whatever the edges we are going to, or whichever the edges we are going to consider, those belongs to the same set, so we are ignoring. Now by using whatever the edges are added, by using those edges, we will get a tree. You please consider, you darken lines are there, HG and then CI, GF, all these you check, there may not be any disconnectivity, we will get a tree with a minimum cost. Now you please observe, from these all whatever the edges are added, draw a tree and find what is the cost of that particular tree. That is minimum cost spanning tree generated, no? What is the cost of that minimum cost spanning tree? So by using these operations, we can implement Kruskal's algorithm and explicitly we will check whether a cycle forms are there whenever an edge is going to be added to our spanning tree. Now whenever we are considering here, algorithm is like this, and A is a set of what is this initial set of edges initially constructed as a pi, and we are checking initially I have to construct a forest. No, for construction of the forest, for each vertex of V belongs to V, do make a set V. Make a set is constant time. So what is the time complexity of our these two lines? Order of V. Make a set means a new set is created just like that. So that's why it's a constant time. But we are doing n number of times, that is V number of times, one number of vertices. So that is the complexity is big O of V. Next, what we are supposed to do? We have to sort all edges, which we have done in the previous example. You please, I arranged all these edges in sorted order. So when we would like to use this sorting, I can use any of the sort algorithm, or I can use priority queue also. Even priority queue also, it has to be considered the respective complexity. So when we are using sorting, the best time complexity of sorting in either merge sort if you are going to take or a quick sort, it will be n log n. Here number of edges to be sorted. No, what is number of edge? E. So we will get E log E I'll get actually. So for sorting or arranging our elements, we'll get E log E. Now what is the next further step? I have to consider one by one edge. So each edge must be considered by us. So outer loop, how many number of times it will be done? Number of edges time. Every edge I am checking, it must be it should it able to added or not, or it is a safe edge or not. We are checking and we are keeping on adding. So that's why we are going to consider the outer loop complexity is number of edges. Number of edges means order of E. Inner loop is there. What we are doing in inner loop, we are checking. Yeah, we are checking here whether the respective parent of the vertices of the edges we are considering both are not equal. Then we are adding to our tree. Then we are using union. So the time complexity, major time complexity based upon the disjoint set implementation and the operations time complexity on union and find set. So we already discussed weighted union can be considered, which time complexity will be order of n only. So that's why based upon that, inner side it will be order of log because it is generating union. No, so that's why order of log n. If it is going to be normal union, if you are going to consider weighted union, then order of log will. That is log n will be there because weighted union makes our tree in a balanced form. So that's why by using this weighted union, we can consider the time complexity here. So what is the total time complexity now? Order of V, we go of V plus E log E plus E log V will be considered. So E log E, E log V. So this is equivalent to big O of E log E, or we can consider big O of E log V can be considered by us because E is equal to big O of V square. In a number of edges must be equivalent to the number of vertices square will be there maximum. So we can get log E is equal to order of 2 log V or order of log V will be there. So that's why we can consider the total time complexity is order of E log V. But even then, implementation of union and find set must be effective. That is, we have to use collapse find rule algorithm as well as weighted unions. Then only it will result like this actually. Okay. So one more example discuss for Kruskal's algorithm. Sorting the edges. All these edges are sorted according to the weight. So 1, 2, 3, 6, 4, 6, 2, 6, 1, 4, 3, 5. You observe here no duplicate weighted edges are there for us. So that's why you are going to consider what is the cast here. Now when we are using one by one, initially we are considering 1, 2 as included. This is the spanning tree, second step after sorting. Next 3, 6. 3, 6 doesn't belongs to this one. So 3 belongs to different set and 6 belongs to different set. Initially all are like this. So we are having 1, 2, 3 like that. All edges are, all vertices are 1, 1 tree. So 3 belongs to 3 set and 6 belongs to 3. Those two are union. So 3, 6 is there. So initially you can assume like this 1, 2, 3, 4, 5, 6. First added 1, 2, accepted. So this edge is added. Union means I'll get like this 1, 2. Okay. Now 2 can be child of 1 or 1 can be child of 2. 5, 6. So 5, 6 belongs to 2 different sets. So I'll consider 5 can be a child of 6, whatever it may be, you can write. So 5, 3, 6. 3, 6 is the least cast. So 3, 6 can be considered. 3 can be child of 4. Third edge is 4, 6. So third edge means 4, 6 is available. So when you are considering this 4, 6, when we are considering the 4, 6 respective place here, so the next vertex is considered as a 4, 6 and 4 belongs to the different set and 6 belongs to the different set that can be added. So this can be added as 4 can be added as a child to 3. So we can consider like this actually. Anyway, you can consider. The next one is 2, 6. 2 belongs to the first set and 6 belongs to the second set. That can be considered. So I can add that edge also. That is 2, 6 can also be added. So you are adding 2, 6. This is also still forms a cycle. Doesn't form a cycle tree. After that, 1, 4. 1 belongs to this set and 4 also belongs to the same set. So it is not same set or a same tree. So which cannot be, because when we are adding the 1, 4, you observe diagrammatically, we will get form a cycle. So 1, 4 added means here. So 1 to 4 is added. Then what happens? It forms a cycle. 1, 4, 3, 6, 2, 4, 1. This will become a cycle. So that's why it is going to be rejected. After that, 1, 4, 3, 5 is there. 3, 5 is 35. So adding the 35 is considered to be as a respective. 3 belongs to different set and 5 belongs to the individual set that can be added. So it forms a cycle here. So coming to the Kruskal's algorithm, this Kruskal's algorithm, as I explained you previously, it consists of disjoint set operations. Here what it is doing in the first step, initially empty, and for each vertex of V, we are making a set, disjoint set is considered. For each edge we are considering and whether the respective trees are going to be having the same parent or not, and we are combining two trees by using union. So the time complexity related to this disjoint set algorithm is going to be E log E can be considered. Disjoint set. The Kruskal's algorithm can be considered as a E log E in general. Otherwise, it can be considered as a E log V can also be considered actually. So this is another example without just by using this you can consider here, and these are the edges A, B, C, D, E, F, G, H are there, based upon which the process is going to be directly included, whether which are going to be added or not. Going on checking the smallest edge is going to be added to our spanning tree or not. If it is added, if it doesn't form a cycle, we are going to add. If it forms a cycle, we are not going to add. This is another example, worked out example is there. Please go through this so that we can understand a bit actually. So same for which prints we consider the same. We are keeping on adding the last one, we will get all algorithm. So by using these two techniques, Kruskal's algorithm and Prim's algorithm, we able to construct a minimum cost spanning tree, but based upon the greedy choice only. So remember that sometimes it may happen, we may not get a spanning tree having minimum cost by using these two techniques. Sometimes it happens, right? So by comparing these two algorithms, Prim's and Kruskal's algorithm, we are have based upon the characteristic construction based upon construction process or a selection rule. The Prim's algorithm is going to be constructed based upon the selecting the nearest vertex. And this process is continued when till all vertices are going to be this process is continued till all vertices are going to be exhausted. So what is the final condition here? The number of times the loop get executed is going to be all vertices are included or not actually. That means n vertices V. And coming to the Kruskal's algorithm, the selection criteria while constructing a tree is based upon the least cost edge, which is not yet included in it. And in second characteristic, cycle formation checking, in case of Prim's algorithm, it will be checked implicitly. We need not write explicitly in our implementation whether it forms a cycle or not. By default, we are checking the vertices are one by one included, which is already included vertices are not going to include further. That itself excludes the cycle formation. But in case of Kruskal's algorithm, we have to explicitly check by adding an edge it forms a cycle or not. For this purpose, a new data structure or a special data structure, disjoint set data structure is going to be used by us so that the cycle formation checking can be considered by us. Of course, we can use any other type of data structure which will perform similar task, but this is one of the efficient data structure to check cycle formation of graph actually. And the last one, time complexities. In general, we can say both are having E log V or V almost if both number of, if it is a completely connected graph, you can use E log E or E log V, etc. But in case of Prim's algorithm, it is E log V if it is a heaping can be considered. Otherwise, if it is a Q as a array implementation of Q is considered, we go off V square. So, but Kruskal's algorithm, depending upon the implementation of the disjoints, a slight variation may be there. It is a E log E or V log E can be considered as a implementation of the data structure is disjoint set data structure is our array data structure actually. So with this, we will conclude that by using either of these two algorithms, a minimum cost spanning tree can be constructed by us effectively and which can be used in our multiple real-time applications. Thank you one and all for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.